Today we have Linda Cook from University of Amsterdam. Linda is doing a lot of work in structural graph theory and also other aspects of graph theory. She did her PhD in Princeton, and then she had a postdoc in Korea. And next, Linda is moving to Utrecht, right?
Yeah.
From September. And today she will tell us about problems that she likes coloring diagrams.
Yeah, so I mean the main bit of, so this is a result from a little bit ago about dichromatic number coloring, but I speak about it here because it's a bit related to what I work on with Bartosz and James and Clément and Marcin and whoever else decide to show up to our meetings. We hope more. And yeah, so there's small result, and then there's many problems I could not solve. That's the positive thing about directed graphs, is everything is open. The negative thing is maybe that everything is quite hard. Do I go like this?
Lost forms.
Okay, it's just like scrollable. Yeah, this is just I did my PhD where everything was induced. I try to mention when something is induced, but I will inevitably forget. So when in doubt, I mean as an induced thing. Okay.
Try to use this now because maybe it just lost focus.
No, it's not working, but I think it's somehow it's not really seeing itself as a presentation because it's a PDF file.
Okay. That's strange.
Yeah. So for
Okay, now it does.
Okay. And so a thing I've gotten quite interested in the past 3 years is what makes chromatic number big, and we have various regimes to approach that. For minors who are doing Hadwigers, I'm working more on trying to understand it based on induced subgraphs, which I didn't ask, but I assume everyone knows. If not, please object. And for this, the regime is basically, we have a nice result by Erdős that we know that there exist graphs with arbitrarily high chromatic number and no short cycles. And so if you want to just forbid some graphs to get bounded chromatic number, well, you know you have to forbid a complete graph. And that's inescapable. And then by Erdős, we know you also have to forbid either infinite list of things, or if you want finite, it's a single tree. And so I'm using in this column here as shorthand, it's chi bounding if there exists f such that 3D has I mean, it's a bit of an abuse of notation here, because right now I'm considering D to be oriented graphs, so it doesn't have a directed cycle of length 2. And I mean the chromatic number to be the chromatic number of the underlying graph. You're not thinking about the directions, and also the clique number is also just the size of the largest tournament. And so for here, we have positive answer oriented stars. So for if you're not considering direction, this is kind of the difficulty of this setting. For the non-directed case, we have many more results. But here, since you want it to be induced and you also want the orientations to match up, everything becomes quite difficult. So for oriented stars, if you just want to forbid stars, this is just Ramsey theory, and you can say, okay, if you don't have a big clique and you don't have an induced star, then your degree can't be too big, because either in the neighborhood of every vertex, you will have a big stable set and a big clique. But when you want to forbid something instead that looks like this, say, you cannot really do this trick. You need to do something much more clever. So it really is like a serious result already, which is a bit sad. And then the other thing is this kind of setting. So in graphs, we conjecture that if we forbid any tree, you get chi-boundedness. For directed graphs, you already break down for paths of length 4, which, so the first answer, this is from shift graphs, and this is a result of Kierstead and Trotter, which I think is an adjustment of Tut graphs. And then what's a bit surprising is that for these two, it's actually, they are in fact chi-bounding. And I just make as a small remark, they're kind of the same case, because if you say if H is chi-bounding for some digraph H, then so is H hat, where H hat is obtained from H by reversing all H. It's all edges reversed orientation. And so we have almost a complete characterization. This was one of the reasons I wanted to talk about it here, because it's one of the nice applications of, you can now say the name because I will not, of master students of Bartosz's work, a nice construction that gives you another no answer for a path on 4 vertices. And then after this, it's almost, since we know already these are no and here are no, we cannot have much more. So for paths, this is the only open case. Yeah. And then that also, of course, means that basically for everything else it's open. So these guys, I just do it with my hands. So this is a minimal open case. And again, since they're made from reversing each other, they're kind of the same case. And then for these guys, you can get another minimal case by, you can clone the leaves on the bottom. So add more edges like this and more edges like this, and then that's also not known. But for everything else, the answer is going to be no. So it would be really nice to get either a positive or negative answer to either of these. James and I are in some degree of disagreement, because I don't believe that these should be chi-bounding, any of these brooms. And I guess you've indicated you do, so you will make one of the two of us happy, regardless of what you prove on it. And yeah, this was just a remark about the orientation of edges. So basically, the problem's almost resolved for regular coloring. So instead, we want to go to this pretty standard variant of directed coloring called dichromatic number, which you, instead of coloring into stable sets, you partition into acyclic directed graphs. For me, it's quite nice because like acyclic directed graphs have really nice properties, and they are, in some sense, the stable sets of a directed graph. And yeah, so this, for example, would be a partition. It's maybe not so easy to see, but if you just look at the edges, they're all acyclic. But of course, this is not a coloring. And for example, here, we can get something that has chromatic number 6, but dichromatic number 2. And then the other reason I find this concept to be quite natural is that the concepts collapse if you replace every edge with a directed cycle of length 2. Coloring and directed coloring become the same. So one nice open problem about this is we know that the dichromatic number is a lower bound for chromatic number, but we don't really entirely know their relationship, in the sense that we're not sure that if you have any graph with big chromatic number, is there some way of orienting the edges so that you end up with a graph with big dichromatic number. And okay, I've a bit cheated. It is a fun problem from a workshop, but the workshop was in 1979, so it's likely to be hard. Though as far as I can tell, not too many people worked on it, so don't be discouraged. And also, I should mention, even though Erdős is a co-author of the problem, he did not offer any money for it. So yeah. And so some indication, for me, this statement seems very miraculous that it should be true. And some indication that it might be true is the fractional relaxation of it is true. So fractional relaxation is basically you're putting weights on stable sets and you want the full things. It's essentially, if you know integer programming, you're taking like the linear relaxation of it. If you don't know about fractional coloring, it's okay because it's not really relevant to this other than the idea that this is a strong indication this might be true, because now if you're looking for a counterexample, you have to look for a graph with a class of graphs with arbitrarily high chromatic number and bounded fractional chromatic number, of which there are very few known constructions for it, and for the ones that are, like, it's been thought about, and we don't find we can't seem to prove that there's an orientation that has that there is no orientation with big dichromatic number. So maybe after this result, it's probably true. And I should also mention that this result is using a lot of the probabilistic method. It's like not too bad of a proof, but we don't really have like, as a structural person, I always like something that I can like bite more. And for many of these things, we don't really have a result we can like eat. And so this is here's another fun problem of workshop. And this one, I was alive during the workshop. I wrote the technical thing on the slide, but for the non-technical workshop, it's like, if you give me a digraph, is there always going to be a way for me to delete some arcs of it however I want, so that the dichromatic number stays big, but I kill all directed cycles of length 2. And as far as I can tell from the workshop, I don't actually remember, I was there, but nobody really worked on this because we very quickly realized that, okay, if this is true, then that is true, and like this guy is famous, so maybe it's bad idea to work on it, let's work on something else, but actually it might be fine. And the other thing I should mention is that he didn't just ask for 2, he asked, what about length 3? And I really think no one worked on it. I thought about it a little bit with Hidde Kurz when he was visiting. And we were also wondering if at any point it gets easier if you just say like, okay, maybe I don't want to get rid of 2, but I want to get rid of cycles of length 2, 5, and 7, and 8. Maybe at some point this becomes easy. And the answer is like a bit yes, if you take like an infinite list. There's some easy cases. So these are various results. Some of them are like by Bondi, and there's older ones, but the strongest in this genre is from Chen Ma and Zhang in 2015, which says that if you have big dichromatic number, you have to, as a subgraph, contain a cycle of length p mod q for any p and q. So one thing we considered but didn't think of that I also think could be a fun problem is if you have big dichromatic number, do you as a subgraph have to contain cycles of k consecutive lengths for a fixed k? And then a problem that's also would be quite interesting, but probably very hard and scary would be, okay, you say it has to have a cycle of prime length, because this is doing arithmetic things, but then that I would not want to touch. Anyway, this was just a bit of a tangent. The main thing I'm going to talk to you about is this much more Gyárfás-Sumner-esque regime for dichromatic number. So I spoke briefly about subgraphs with dichromatic number. Now we ignore subgraphs again. Everything is induced again, which is the way I like it. And so there's a theorem of Harut, Yunan, and Mohar that's essentially the digraph equivalent of the Erdos theorem of high dichromatic number. So this is actually a little bit of, there's a typo in this slide. They proved a much stronger statement. So for every graph, for every t, I can't cover up that for you, but I can verbally say, so for every, there's exist digraphs with arbitrarily high dichromatic number and no small cycle in the underlying graph, so not necessarily directed cycles. So here I wrote directed cycle, I should cross out that word. And that also includes digons, of course. And so that means that when you're in this setting where you want to bound the dichromatic number and you're just forbidding not many things. If you forbid something that contains a cycle, again, in the undirected graph, you're in trouble. So we're still in this Gyárfás-Sumner setting where we want to be forbid forest, except now it's orientations of forest. And here I give some bit more justification why we get to do cliques. So basically, if we want to forbid things and get bounded chromatic number, if we want a set of size 1, it has to be a vertex. Set of size 2 is also not interesting. The only minimal set is you forbid an edge, and then you forbid a digon-directed cycle of length 2. So that's also a bit stupid, because you just don't have edges. And then the first interesting case is 3. And Aboulker, Charbit, and Naserasr, when they introduced this regime, proved that if you're forbidding 3, you have to forbid like a stable set, or you forbid a directed edge, which essentially means that every edge is a digon. So then you're just talking about graphs and coloring, and we already have those problems. Or you're forbidding a digon. And for the case where you're forbidding a stable set as an induced subgraph, that has been fully done by those authors. So really what remains, if we want to be different from graphs, is this case where we're forbidding the digon. So for the rest of the talk, we're always going to be forbidding digons. And so they further showed that, like...
Sorry, because I got lost. What is open here?
So the, what 3 digraphs can we forbid so that we have bounded dichromatic number when none of the 3 is a stable set or just an edge? So in this case where we know one has to be a digon and the other 2 are something else, then it's open. And then this is, again, if you remember this, the first line, I think, is fairly clear. If you remember that, okay, we know we need to forbid an oriented forest, because for forbidding something that's not a forest, we end up with this no short cycle and a high dichromatic number case. And we also need to forbid some tournament, because the class of all tournaments also has unbounded dichromatic number. Oh, God. And they further showed that actually, in fact, you either have to forbid a transitive tournament, or the forest you're forbidding is the disjoint union of oriented stars, which I do not find to be a terribly interesting class of stars. Okay, everyone, like it's K1T, I hope you know it. It's not a terribly interesting class of graphs. There's been some work on it. There's, I don't think, a full characterization in this case. And so every large enough tournament contains a transitive subtournament. So this is equivalent to saying that the clique number of the graph is bounded. So it becomes really analogous to Gyárfás-Sumner, that you have bounded clique number and you forbid a forest and you want the dichromatic number to be bounded. And they conjectured that the converse is true, but they found it false. There's a counterexample for you are forbidding a tournament that's not transitive and some disjoint union of oriented stars, and you still have unbounded dichromatic number. But the part that's still open is this case where the tournament you're forbidding is in fact transitive. So to state it more properly, this is the conjecture that's open. So basically, you bound the size of the largest tournament, you forbid an oriented forest, and then you want the dichromatic number to be bounded. And yeah, so now we can kind of compare. So chi bounding, I erased the definition. So for di-chi bounding, I want the same definition, but I want that chi to have an arrow over it to represent the dichromatic number. So hopefully it's okay. So one thing that's clear is, well, one, I already gave you the result for non-forests from Harut, Unan, and Mohar, and also chi, unfortunately, the directedness of the chi is covered by the zoom bit, but there's an arrow over that. The second column is chi, and if you're chi bounding, you're also chi bounding, because chromatic number is always an upper bound for dichromatic number. And so this is kind of where it starts to differ a bit. So for P4s, it doesn't always work. And then our result, which unfortunately was already non-trivial to prove, is that it works for all orientations of P4s. And otherwise, essentially everything is open. So it's for any orientation of a forest where that forest has more than 4 vertices, and it is not a star, it is open whether that forest is chi bounding. And it's actually even a bit more than that. So this is all open. But actually even the triangle free case is almost like always open as well. So if we're saying, this is the result I will talk about. So if we're saying like, okay, you can assume there's no tournament of size 4, and I'm forbidding an oriented forest where F is not a P4 or a star, and also F is not exactly the directed path of length 6, then we also don't know if the resulting class has finite dichromatic number, which is quite remarkable. I personally do not, the conjecture is that this should be true for you forbid any tournament of, like you make a bound on the size of the tournament, and for any oriented tree, the resulting class should have bounded dichromatic number. And what we know is very little. I personally do not believe this conjecture, so it's a part of why I wanted to present it here, because as I know, this is the department where people like to break conjectures, and I hope that maybe someone can break it and we can be free. And so for the rest of the talk, I'd like to talk a little bit about how we do this result. It's not terrible, but it's already like, for graphs, if you're proving something's P4 free is chi bounded, it's like a cute homework exercise, and this is definitely like not homework unless you're giving a lot of hints. And I mentioned just briefly a bit about the history, so I already mentioned this for these two kind of non-alternating, non-directed orientations of P4, they're known to be chi bounded and therefore also chi bounded. And so there's only, up to reversing the order of all edges, there's only 4 orientations of P4, which are these guys, maybe. And so for these two, Alex Scott, Murray Chudovsky, and Paul Seymour showed that they're chi bounding and therefore also chi bounding. For the other two was open. And I should mention they got some partial progress in both cases. So there's a nice result of Aboulker, Charbit, and Naserasr for the directed P4 free and K4 free, and also for alternating P4 and excluding the transitive tournament of size 3, Steiner got that there's a finite bound. And so our contribution was that basically we can fully handle these other 2 orientations. But actually our proof works the same, like it also gives you these 2 orientations as well. You just basically, there's an annoying page for finishing the proof for these 2, and if you skip that page, you get the proof for these 2. And then this was the final result I mentioned with the P6. So if you're triangle free and you're P6 free, you have bounded dichromatic number. This also is very heavily relying on being triangle free. They do a trick like, okay, if you have a hole that's directed, I think, and then you have a vertex that has neighbors on it, well, it can't be complete to the hole because it's triangle free, which means there's ways to kind of start building your path from it because the whole thing is connected and you're skipping every other neighbors, and then they go like out a little bit through the neighbors and second neighbors of the path to analyze this, and then they do an induction. It's really, really a very short, smooth proof, but I don't personally see any way of extending that proof to get it even for K4 free. There's a couple more results if you're allowed to forbid multiple forests, but other than that, this is open, and it's really sad state. So I really hope someone can find counterexample, because for positive results, a lot of people have tried and they haven't really gotten anywhere. And then I was hoping I could just turn the projector off and sketch the proof a bit. I think this is also, so this is now the part where it's like only interesting if you're interested in working on it. So this is also a good point to have an intermission and escape if. The problem is there's peer pressure whenever the speaker is like, oh, you can escape now. No one ever does it. Because...
The problem is that it's recorded and then put on YouTube.
I see, but they don't know. They're not going to be on video escaping. Is there, this is the erasing system?
Yeah, it's very sophisticated. How it works.
So the main trick for all of these dichromatic number proofs, and basically why they don't really work for a chromatic number at all, is we do something that's called sometimes a dipolar set. Sometimes you also see it called a nice set, where so S is dipolar if there's never a vertex that has both an in neighbor and an out neighbor to the rest of the graph. So it's basically just a block here S within a larger graph, and you can divide it where some may have no neighbors and the rest, that's fine. But if you have neighbors, either you're only out or you're only in. What you don't have is something like this. What's up?
Yellow diagrams?
No, there's no digons anymore because we know we have to forbid them to hope for dichromatic abundance, so I'm just operating under the underlying assumption there is no digon. Thank you. And so there is a lemma by Aboulker, Charbit, and Naserasr from 2020 that for all induced sub d prime of p, d prime has a dipolar set, a bounded dichromatic number, then the whole thing is bounded. So if you and all your induced subgraphs, if you're always going to find a dipolar set with bounded dichromatic, the whole thing is bounded, and basically the proof is choose D minimal. So suppose you have a minimal counterexample. So by assumption, it's so if this is your D. By assumption, there's some dipolar set living in it, S. And we know the rest we can color with 2 gamma colors. So we have this palette of size 2 gamma. And then we divide S into the ones that only have positive edges in the rest, and the ones that only have in edges in the rest. And each of this, because all of S is gamma colorable, so we can use a palette of gamma here and a palette of gamma here. And then there's no way you're ever going to get a monochromatic cycle, because this is like within each is proper coloring. Here, this whole thing is only gamma color and switching, and if you have a cycle that's going like this, well, you don't have to hit both the positive and the negative version, so you're fine. And that's every proof of showing that things are Dai-Chi bounded that I've seen uses these dipolar sets and does induction on it. Possibly the proof that I mentioned by Raphael Steiner does not. I didn't read it, but every other proof I've drawn on the board does. And so this is going to be our goal for the P4 thing, just get a bounded Dai-Chi set. Just for concreteness, I'm going to say that we're P4 free, we're P4 equals. This one, most of the proof is actually not dependent on what orientation you're forbidding. As long as you forbid one, the same proof works, but I found that for talk, it's more concrete to be like, okay, this is a specific one. And then we're going to choose the, So we have a P4 free D, and we're going to let omega equal to omega of D, where that's the size of the largest tournament. And we're going to say gamma is max prime over all directed P4 free D prime with omega D and omega. And we're going to inductively assume that this is finite. And so now there's one trick that if you work in chi-boundedness at all will be very boring to you, and if not, it will be a reminder. So observation for all V, P, the dichromatic number of the graph induced by the neighbors of V is going to be at most gamma, and that's because the neighbors of V cannot have a tournament, a clique of size omega in it. So you just apply this.
So Linda, just because I stopped for a moment over there, now I'm trying to catch up. Now you studied P4 free, P4 is oriented transitively.
Directed, yeah.
One direction. And then you say omega is D is the digraph, which is P4 free.
Yes.
Omega is the clique number, and this next thing I cannot read it.
It's supposed to be a gamma.
Gamma, okay, good.
My Greek alphabet is not strong, and that's just the maximum chromatic number of any digraph that's P4 free with smaller clique number.
So by induction you have it.
Yeah, and inductively we assume it's finite.
Okay,
yeah.
And now observation is that where the vertex of D, the neighborhood. Yeah, and that's usual. Okay.
Yeah. Mm-hmm. So what this means is when we're trying to bound the chromatic number of something, we're quite happy to just ignore a finite number of vertices and their neighbors. And that will come up a bit. So I'm going to give you a lying proof, which will assume that we have a transitive tournament, not strongly connected tournament of size omega, and then I explain to you how we do it in the case that you don't have it. We don't actually have to do these things separately, but it's a bit illustrative because it's a simpler case. So suppose C is omega tournament and strongly connected. Okay, so I'm going to look at C, and then I'm going to look at the neighbors of C. And so there's the neighbors that have just in neighbors, the ones that have just out neighbors, and there's the ones where every vertex has both an in neighbor and an out neighbor in C.
What is an omega tournament?
A maximum size tournament. Omega is a number, it has a tournament of size omega.
Oh.
Yeah.
Makes sense.
yeah, it's a bit sloppy with notation. I also should note, you can stop me if it's confusing, but I'm often conflating chromatic number of a set of vertices and the chromatic number of the graph, but since everything in this setting is induced, I'm allowed, but if you don't work with induced things, that tends to be confusing. So X is the set of vertices that have both an in-neighbor and an out-neighbor to C, and are not in C. And then I'm going to claim that the closed neighborhood of NC union X is dipolar. So to draw it, we have the neighbors of C, and then we have some more vertices which are neighbors of X but not C, and in the end our dipolar set is, we're choosing, colors aren't so visible, but we're choosing this, all of NC, and all of C.
So X are just those which have both in and out.
Yes, yeah.
And this N is again, the operator in the claim is the same operator, so also those that have in and out neighbors in C union X, which means now just an X actually. Because X is defined to be N of C.
No. This is I drew the entire neighborhood of C and tried to draw X separately. Yeah, I'm just a bit sloppy with my handwriting. And all of this is. And so X is the ones that have both in and out, but there's more neighbors. And the dipolar set is this entire thing.
Oh, I see.
Okay, yeah.
There's one of those.
Oh, yes, good point. Thank you. And so this is basically by just proof by staring at it. I'll do it quickly. If you don't understand it, it's maybe not okay because it's not very interesting.
But to prove that something is dipolar, you need the context of the rest of the graph, yeah? Because,
yes.
Okay.
Yeah. So yeah, here's the rest of the graph. So we're imagining that we need to show that for every vertex, if they have neighbors in the rest of the graph, they only have neighbors going one way. So for C, we're safe because we've included all neighbors of C in it. So we really only need to consider this set. And because for here, we're safe because we have all the neighbors of this in it as well. So these guys were good. And then, so for this set, can just suppose that there is an in neighbor and an out neighbor in the rest of the graph. We don't know, maybe there's an edge here, it doesn't matter. And we know by assumption that it has to have some edge in X. And again, by assumption, X has both an in neighbor and an out neighbor in C. And so if you look closely, it doesn't matter how this edge is oriented, no matter what, you get a directed P4.
Actually, whatever orientation you want.
Yes, in fact, yes. So this beginning part of the proof is entirely the same for like forbidding, this set is still the same dipolar set for forbidding any orientation of a P4, but and so for the next thing is to assume, I mean, these two cases are symmetric, so we can say this one has both an in neighbor and an out neighbor in the rest. And here we need to see like, okay, so we're looking, so in particular, does it have an out neighbor in the rest? And here this vertex that I've drawn cannot be adjacent to all of C because C is a tournament of maximum size. So it's not adjacent to something. Maybe this. But the whole thing is strongly connected. So somehow there has to be a path going from this vertex into the tournament, which means in particular there's some edge that's going to be adjacent to a neighbor of, say this vertex, call it V, where the other end of the edge is not adjacent to V. And then that's your directed P4. And same, the other case is symmetric, you just do it with edges going in. And so it's dipolar. And then to see, what's up?
You use only connectivity for which reason?
For this reason, to force that,
Yeah,
to force that it's a path. And that's in fact the only, we're not really using, that's sort of the trick, we're only using that it's strongly connected and it contains a tournament of maximum size. We don't actually need that it is a tournament. Thank you. Yeah, so now if we bound the chromatic number of the set, we're done, so we're happy. And this we can basically bound by repeatedly applying this observation that we're allowed to get rid of the set, a bounded size set and its neighbors. So, so we're gonna observe that the dichromatic number of n C, so C and all of its neighbors is at most C times omega plus 1.
May I suggest to use white?
Yes, sure. Yeah, if you're colorblind, it's really terrible. So if we want to bound the chromatic number of the whole thing, the only thing we really need to worry about is this, all of this has bounded chromatic numbers, so we just need to worry about bounding the number of this set. And for this, I need to give the set a name, which is going to be y. Hopefully, you can still see it in this drawing. And claim y is at most 2 gamma. And so we can assume that our graph D is minimal with respect to the leading vertices. And also x does not equal empty, because if x equaled empty, y would be empty, and then the whole thing's silly. So there exists, so we have x, we have C, vertices and x have an in and out neighbor. We have some x and x. And we have y. And I'm going to claim that nx intersection y is dipolar in P in the graph induced on y. And so suppose that it isn't. So that's going to mean supposing that there's some y, both an in and out neighbor in the rest. And in particular, this all came from neighbors of x. So the in and out neighbor, they might be adjacent to each other, we don't know, but they're not going to be adjacent to x. And also x has both an in and out neighbor in C. So if you look closely, you see, like, okay, no matter how we orient this, we're in trouble. We're going to get a directed P4. And then it's also easy to see that ny is, by this observation, kind of nx is at most gamma, so we just apply this lemma about dipolar sets to get the bound on the chromatic number. So that's the complete proof if you happen to have a tournament that is strongly connected. And the rest of the proof is kind of, you try to simulate this idea. So if you don't have a strong tournament that's strongly connected, we just add a path that makes it strongly connected. And we want to choose it to be minimum amongst all possible choices of that path. And then we basically define the dipolar set in the same way. But we have much more work to do because we don't know. Here we kind of knew that, well, we know that the size of C is bounded, but if we have C plus some extra vertices to make it strongly connected, we have no control over this being any fixed constant amount of vertices. It could be arbitrarily large, so we can't just say like, okay, we take the neighbors of everything. We need to be a bit more clever, and that's like the bulk of the difficulty of the proof. So to write some things down, just saying it verbally, ignore. So something that we call a path minimizing closed tournament. Tournament K of omega So to say informally, we're just taking a tournament of size k. We don't know if it's strongly connected. If it's not, we know just because it's a tournament that if we, it'll give you a total order of the lowest connected component. So if we take a path from the lowest connected component to the smallest connected component, maybe the path intersects a bit and comes out. This will then make it strongly connected, and we want to choose the smallest such available closed tournament. And so if we just, in our previous proof, let C equal K union P, the same definition, it's still dipolar, because actually like the exact same proof works. I was just adding the assumption that it's strongly connected to illustrate a point. The only thing that becomes difficult is bounding the chromatic number. And so, and so I'll do some adding. So N C union P, so the closed neighborhood of, sorry, C union X is dipolar. And the chromatic number of this X, it's going to be at most chi of N of K, close neighborhood of K, plus chi N of X, chi N P, plus the chromatic number of P, which is almost 2. So this guy, it's, again, it's a neighborhood of a bounded size set, so it's just omega times gamma. This X, by the same proof, it's 2 gamma, and then here is the difficult point that you have to somehow, you can't just say, I mean, sure, it is P times gamma, but you have no control over the length of P, so you have to do something more clever to repeat vertices. I'm like quite a bit out of time, so I can also describe how we do this offline. This is kind of giving the main idea of the proof already, because kind of the main tricks is we use that color thing, and we not just choose any tournament, but sort of the best one in some sense, and between the two of these things we have enough structure. There's quite a lot of, this path is not necessarily induced, but there's quite a lot of rules for how edges have to go between them that allow us to repeat palettes of colors amongst vertices of neighborhoods of different vertices of the path. Okay, yeah. I feel bad to have hostages, but yeah. Yeah, I can maybe explain a bit more of the proof, because there's like 1 or 2 nice ideas, so. So for P, we need to just introduce some notation for P. So we're going to do P1, P2, PL. And for P1 and PL, we're just going to take their neighbors and just color them with gamma colors. We can do this bounded number of times, it's fine. And for the ones with neighbors on the inside, we can notice there's a couple patterns that are a bit silly. It's like quite a stupid observation, but basically if, so I'm some neighbor, if this is somewhere pi plus 1, and then pj. And pi is somewhere in the inside. So if I'm a vertex that's a neighbor here, and that's an out neighbor of this vertex, and there's someone else, maybe it's in neighbor, maybe it's out neighbor of j, we don't know, and it's not adjacent to this or any of the earlier ones, then we can't have an edge like this, because then you get a p4 like this. And similar for the opposite way. So what we do is we sort the vertices by where they get their first neighbor and where they have their last neighbor on the path. Where first and last are defined by this ordering of the vertices on the path. And if your first neighbor, so if these first neighbor P, and the arc is oriented pi to v, then we're going to call it fi minus, and then similarly,
Please use white.
Okay, yes, sorry. Okay, so we're going to call fi the set of vertices whose first neighbor on P is pi, and li is the same thing, but last. And so for the fi's, we divided into fi plus and fi minus, depending on the direction of that edge. And basically what this observation says is that, say, this way means fi minus, that fi minus is has edge to j. No, other way around. Because otherwise you get this P4. And what that means is we can color all the fi minuses with the same palette of gamma colors, because there's never going to be a directed cycle that is contained in the fi minuses, but it's going between multiple fi minuses. And we have a similar thing for li plus, it's just the complementary thing. So f2 minus union fl minus 1 minus this. And you do the same idea for for the last neighbors, so like L2 plus union S1 plus gamma colors. And then let's call R what's left over, and this I really don't want to get proof because it gets a bit annoying. But basically at this point in what's in R, we have quite a lot of structure about how their neighbors to P have to go, because we know they cannot be in any fi minus or li plus. So their first neighbor on P has to be going towards, the edge has to be oriented towards P, and the last neighbor has to be going out. We don't know what happens in between. There can be anything. And this is enough structure for us to say that, okay, if we're going to suppose that... Oh yeah, it should be, yes, sorry, yes, exactly this. Yeah, so at this point, if we look at R, we can say that, so we can show that omega of R has to be less than omega. Because if it is, basically the structure gives you that there's going to be a lot of short paths on the graph between two vertices in R. If you have some path that's some vertices VA that have an arc like this in R, then there has to be a short AB path. This is essentially just case analysis and like your P4 free, and you have the structure of the things, so it has to be getting some path using either the path itself or back edges along the path P. So a element of E of R is a short AB path. And so if you have a small clique, if you have a omega clique, or tournament, sorry, J in R, well, if it's strongly connected, you already have a contradiction because you started off with something that's not strongly connected. So you look at all the components of it, all the strongly connected components, sorry, and so maybe everything's like, all these edges you're always going up. So that means there has to be an edge like this. And then you choose this to be your B and A in the lemma, which gives you that there has to be a relatively short path connecting these two up. And in particular, that path, so if we call this, like this tournament is J, and this path is Q, J union Q is less than K union P, which contradicts the inductive assumption. And that's the complete proof, because since omega goes down, that means the chromatic number of this is at most gamma. Yep, that's the proof. I'm happy to answer any questions or talk more offline.
Thank you.